Okay, good morning, everyone. Welcome to this tutorial. So my name is Bereket. I'm from the University of Luxembourg. And today I'll be doing this tutorial on computational methods for designing human-centered recommender systems. We'll be taking a case study approach between visual arts and healthcare scenarios. So quickly, what this course is about, or it's going to be like a 3 hours lecture. We started a little bit late and there's quite a bit of content that I have to cover. I planned to cover, so we'll see how far we can manage until the deadline. So ideally, this course is for you, essentially, if you are new to recommender systems. How many of you are new to RecSys? Okay, good. And if you work in industry, focusing on human-centric aspects, that's also for you. And if you are a researcher or practitioner interested in human-centric aspects of recommender system, and if you are also a student, this is pretty much introductory through a case study approach. So even if you are experts, which I think most of you are, you might learn something, I hope. So yeah, how many of you are familiar with machine learning? Machine learning, everyone? Okay, yeah. Yeah, so we'll see examples in Python. So if you have familiarity in these topics, it would be helpful. All right, so this is pretty much the outline I planned to cover during the half-a-day program. We will start with a brief intro into RecSys. And yeah, I will drive this home with some notion of cyber, physical, and social systems. We try to look at why we care about human centricity and how we can achieve human-centered recommender systems pretty much. So yeah, if you want to have access to the slides and to the notebooks, you can quickly scan this QR or go to this URL so that you can follow. The QR, okay. Okay, so let's start by talking about some philosophical, per se, concept that is cyber, physical, and social systems. How many of you have ever heard this term, cyber, physical, social systems? No one. What do you think it means? Or, okay, have you heard of cyber physical systems, or CPS? What do you think it means, CPS? You have a cyber, you have a physical, and you have a system, right? And when you add a social, you have cyber, physical, and social. If you do look at the textbook definition of cyber physical systems, a system composed of a physical component, which is monitored by a cyber component. It's essentially sensors, actuators, any kind of robotics devices that have a physical component and controlled through some kind of software. And when you add social, this is pretty much a paradigm shift from the pre-existing concept of cyber physical systems. Is that a question? Okay. Okay. So this is a major paradigm shift. So of course, these devices are created for use by humans, but we want to understand what is the impact of these devices on humans and the impact of humans on vice versa. So this paradigm shift is essentially led to the development of what we call them smart systems, smart homes, smart museums, to create more of human centricity, let's say. So in the previous concept of cyber physical systems, this is mostly concerned with computation, networking, and physical processes. And basically, human was missing. So we want to put human at the center of this design. So we add the social component essentially to enhance interaction between humans and these devices, right? So the focus was essentially human was missing there, and we want to focus on humans and the interaction between humans and these devices. So we had a social, and then this is a paradigm shift to study and investigate this relationship between the two. So there is a lot of literature behind cyber-physical social systems, but why is it interesting? Because of the term social. We all know have cyber-physical devices like smartphones, your VR glass, your computer. It's a cyber-physical device. But we want to have some notion of social aspect. So we introduced the social concept and we call it cyber-physical social systems. So the social component, essentially, we want to put human in the design paradigm at the heart. But what is a social interaction? How do you perceive what is a social interaction for you? Any guess? This can be social interaction, right? So you look at the textbook definition from the theory of social interaction, it's a situation where behavior of one actor is consciously recognized by another actor, actors, humans, of course, and influenced by, at the same time, the behaviors of other actors, right? Okay, think about a social interaction between humans. You and I are conversing, we're talking. It's a social interaction, right? From social science, Norman's model of interaction states that tells us that in any kind of interaction, human beings, we generate 3 layers of interaction responses: emotional, cognitive, or behavioral responses. And we understand, we detect, reason, and adapt to these responses from each other because we are equipped with similar, let's say, sets of sensors or information processing units, right? But when you think about this kind of interaction between humans and the devices, fundamentally, this is missing. And that's what we want to do. You might argue now we have a lot of evolution in AI today, in linguistics. ChatGPT is pretty much a rather older examples, but we've had a lot of developments in AI to mimic these small pieces of human intelligence. But to truly mimic this kind of social interaction, the one we have between us, this is still an open challenge. We cannot, or we don't have yet this kind of social interaction in machines when you think about human and machine interaction. Let's look at our evolution of interaction. So when we were hunters and gatherers, starting at the early age, we have humans interacting with a physical device or a physical component, right? This is like a time from the first industrial revolution to second industrial revolution. And with the development of compute, we start interacting with a physical object with some notion of cyber component or software added to it, right? So this is what we call human interacting with a cyber physical device first. And then we want to evolve this interaction into a cyber physical and some notion of social component embedded or integrated in it. So this is Industry 4.0. Even the one we have, Industry 5.0, we are propelling towards with AI and all automation towards more human-centric or mimicking some intelligent aspects. So this is what we are currently calling the evolution cyber-physical social system. So it's a physical system or a physical space where humans interact with others and at the same time interacting with physical devices. And this is what we consider as CPSS currently with all the latest technology advancements that we have. But a social component truly, in a sense that humans are interacting, is deeply ingrained in these concepts of emotional, cognitive, and behavioral facets. Sorry.
Bye.
So the audio is fine online? Can you check? It's fine?
Yes.
Okay, let's go back. Where were we? So we were looking at the evolution of interaction, right? So with the addition of human cyber component or some softwares, we started interacting with devices that somehow try to mimic some sort of human intelligence, which we perceive as social to the best of their abilities, right? And this is where we are. But a true social interaction is really deeply ingrained in these components of social interaction theory, emotional, cognitive, and behavioral facets. And that's kind of what we want to mimic ultimately. And a famous quote from robotics, social robotics, states that designing a human-centric machine effectively requires recognizing these human-like traits, or at least a metaphorical attribution of these components to machines. And this paradigm of CPSS eventually wants to have is a device with some sort of social component, however that is implemented. So whether should we actually do this, or how do we get there, is still, can be debatable. But why am I introducing this notion of cyber, physical, and social component, which takes systemic theory or notion of systems? It's very powerful concepts to model systems and interactions. And we will see how this is relevant in the later sessions to model interactions and particularly recommendation tasks. So let's pause about CPSS for a second and talk about the concept of personality in social interaction. So when I say personality of people, what you understand is what? What is personality for you? Anyone? I think that's a very huge concept. It is, but what do you understand when I say personality? What's your personality, or? Sorry?
What is stable and unique about a person?
Yes. If we look at also textbook definitions, for example, this definition states personality describes unique patterns of thoughts, feelings, beliefs that distinguish a person. And it's supposed a combination of your biology and your environment, which kind of makes you who you are, right? So now what is the role of this in social interaction? Essentially, the quality of interaction in social context depends on how well do we know each other, right? So if I know what you like, what you don't like, your preferences, your limitations, I can adapt to you. The same is true when we think about designing machines or social interaction between machines. So recognizing these individual preferences, needs, limitations, opportunities becomes necessity in this social kind of interaction design between humans and devices. And so this kind of positions the concept of personalization at the heart of this paradigm shift. When we bring the social component in CPSS, the added S essentially has a lot to do with personality and personalization. And personalization, of course, is not a new concept. It's been researched since the 90s. But what comes out of this evolution is essentially data, right? We evolved from interacting with objects, with machines, some kind of software component, and now we're trying to mimic some human intelligence and trying to model some kind of social interaction, human-like interaction with machines. And basically, we kind of started to create huge amounts of data. And today, our actions on the web kind of create a huge content, right? So according to some statistics, we are creating more data every year than the entire history of humankind. And our options on the web are essentially limitless today. We have very powerful tools that allow us to create, to interact, to develop more things, in turn leading to the creation of more content, which can be ingested back into creating super powerful models, which is great. And then we have multiple applications, multiple tools that we can use to do different things, which is great. This abundance is nice, but it also creates a problem. You have multiple options to do multiple things. Think about language models. You have all kinds of language models coming out of all these big tech companies, and they're trying to do pretty much the same thing with different level of performance, for example, which is great. And what model is best for your task? You have to make a decision, right? Just to give an example. And this happens everywhere. You have like all kinds of services, service providers. You have to make a decision. And it's becoming more and more challenging. It's great to have multiple options, but how do you know that the choice you make is the best option for your task? Or maybe you make a decision and you might suffer from the fear of missing out, like maybe this is not the right option. So in an ideal world, what we want to have is essentially still maintain this abundance and still have some sort of certainty. And this is where kind of recommender systems come in to help you make a decision. So RecSys or recommender systems are pretty much basically algorithms that help us make decisions. So essentially, it has a lot to do with decision-making process. And we're talking about algorithms which allow us to decision on purchase, decision on what music to watch, movies, news, whatever. These are like classic examples of RecSys and some old statistics. For example, here, the consumptions on some of the major platforms are also attributed to the power of the recommendation systems that they use. So this is kind of an example of online or the classic kind of recommendation tasks. And we have the bigger picture of personalization, which also entails a lot of things, adaptation. But RecSys is kind of within this domain. So if you look at recommender systems, you have data and machine learning model and predictions, right? And essentially, the data is like user preference, the classic way, and then you have recommender systems, and you get recommendations. So user preferences are essentially can be explicit or implicit feedbacks. For example, likes, dislikes, or implicit inferred from your interaction based on your previous purchase, what you might like. So we take this information, we use some kind of models that could learn patterns from this data and then make some predictions about what you might like, so on your future behavior. So this is the classic recommendation system or RecSys pipeline, right? Okay, so just a quick overview of what paradigms exist to actually do recommender systems. So in literature, we have 3 common approaches to do recommender system. We have collaborative filtering, content-based, and hybrid approach. So I assume most of you are familiar with this, but we can just quickly go through each of them before we start talking about human-centered approach. So first, collaborative filtering. This essentially is based on the idea of similar users like similar things. So a phrase that we are all familiar with, customers who bought this item also bought this. So the data is essentially user-item interaction matrix. So when you have, for example, a new item or a new user, in this case, we suffer from cold start problem. You have a new user with no interaction information, and you have a new item, nobody has given preference or rating, so you're going to have a cold start problem. One of the limitations of collaborative filtering. Second approach is content-based. As the name suggests, is based on content or the assumption or the analogy between user's profile and content of items. So the data looks like this. So this is based on features. So for example, you have users within the age range between a certain 25 and 35 might like a certain kind of movie. So you use this kind of analogies to make recommendations, and this suffers less from the cold start problem. And thirdly, you can combine these two, and we have a hybrid approach to recommender systems. And most recently, there are also different variations of recommender systems, modern, like for example, multi-stakeholder aware recommender systems, taking into account multiple stakeholders to drive some kind of recommendation for users. And we also have latest LLM-based recommender systems using language models as recommender systems, zero-shot and few-shot RecSys. So we try to cover a bit of this in the third session. But what I want to talk about today is human-centric recommender systems. So basically, there is a common pipeline, a common framework of recommender system design, which is inspired from the classic machine learning or information retrieval. So we start always with the data. So there's this interesting statistics that I saw a while ago. 60% of the time the data scientists spend is actually cleaning and pre-processing. And the actual model training and prediction is kind of very less. But yeah, we're not talking about this today. Our goal is to make a recommender system, right? So we want to build a recommender system. What do we need? We need to train a model, which kind of learns some kind of patterns from the data so that we can kind of post-process, filter, sort, and then deliver this recommendation to the users. And in the end, we evaluate how good is this recommendation using some common evaluation metrics. So these are basically the most important aspects that we care about when we design recommender systems. Of course, data processing matters a lot. But the question is, how good is the recommender system? Right? That's the question we ask at the end. We train a model, we build some platform, and then it gives recommendation to users, but how good is the recommender system? So you have different kinds of metrics to measure similarity, to measure how accurate is the recommendation. But another question that you can ask is, how good is the evaluation metric itself? Or what is the recommender system doing to the user? There can be multiple purposes for a recommendation system. You can design it to do different things. And we want to understand what is the recommender system doing to the user and how good is actually it doing so and so. So what do we think about human-centered recommender system? When we say human-centered recommender system, according to a definition by Constant and Traven, human-centered recommender systems, or human centricity, kind of describes an approach to recommender systems which basically evaluates or tries to understand the characteristic of the user and the characteristics of the recommender system and their kind of interaction. So here, the goal is to design algorithms, but these algorithms should fulfill or better fulfill the goals of the user and also the organizations or the entities or the stakeholders. Did you unmute? Okay. The goals of the stakeholders. So when we say human centricity, of course, we are always have always been designing recommender systems to give recommendation for users. User has always been there. But now we want to understand what is the recommender system doing to the user and how is this interaction affecting the user and the other entities involved? Because there is a lot at stake, especially today. And I want to ask you this question, coming back to what we were talking about in the beginning. Where do we find a typical RecSys user today? Any guess? Online, yes. But where are you now? In a room, right? With your laptop, with other people. You're interacting with me at the same time. What is this? This is what we call a cyber physical and social system, or a CPSS, right? You have a cyber component interacting, and then you have humans interacting with you. So it's kind of a smart world today we live in. Wherever you go, in whatever environment you are in, you find yourself interacting either online or in person, interacting with devices, with people. So we are essentially in CPSS. We're living in a cyber physical and social system, although this social component, however evolved it is trying to mimic some sort of human-like social interaction with us, regardless of the task. So when we talk about CPSS or existing in this kind of virtual environment, you have users existing in the same physical space, like you and me today in this physical room. And the room could have a certain rules that you have to respect and follow. The room itself is a stakeholder that you have to respect, and people are usually not tolerant to respecting these rules. And you have your own objective to come here. You have your own objective to go to, for example, a museum, to go to some venues that are we consider smart. Think of a production line in a factory, which is a smart production line. You have your own goals, and the venue also have its own goal. So this can be conflicting. Again, there are some constraints coming from other people that are existing in the same physical space. Somebody could be speaking loud back then, so you cannot hear me when I'm communicating with you. That's kind of adding some constraint in this interaction, right? So this all adds to this interaction, which makes it rather challenging when you think about giving personalized service in this kind of constrained environment. So making it personalization quite challenging. So one thing is, what you can do is, okay, I need to take into account all these components, right? How do I mitigate this so that I have a seamless interaction with my user when I'm giving personalized service? So you can think about, for example, multi-stakeholder aware recommender system. This is pretty much the goal of multi-stakeholder awareness. So your model is aware of the stakeholders that are in the surrounding of the user. So I respect the constraints so that I have a seamless interaction or a seamless experience for that particular user. So pretty much the notion of multi-stakeholder awareness plays a huge role in this modeling of personalization in cyber, physical, and social systems. So we have seen that there is this question that we started asking: how good is the RecSys, right? And what is the RecSys doing to the users? So human centricity and the kind of evaluation metrics we employ before deploying recommender systems is essentially the key to ensure human centricity. We'll see about evaluation metrics later on, but this is the kind of human centricity or ensuring this kind of seamless interaction between humans and recommender systems or personalization services that we want to create or ultimately design. So we're going to look at now the RecSys pipeline, which is the classic RecSys pipeline. But now we always want to think about humans and the stakeholders around their interaction to make it more human-centric. And then in the end, evaluate this recommender system based on not just how good it is, but what is also doing to the users. What are the users getting from this recommendation? How are they perceiving this recommendation? How are they reacting to it? And that's the kind of evaluation we want to do if we want to achieve human centricity. And this notion of CPSS will basically fundamentally help us to model the environment so that we can drive this kind of human-centric notion in the delivery of recommender systems. So now let's pick up a case study. So for the rest of this presentation, I will give you a scenario, and then we will talk about the problem, try to model it, and then talk about some of the research papers that try to solve this problem in such and such a way. And then we kind of zone out to those computational methods that were used to actually achieve those solutions, and then come back and look at the foundations or the results from coming out of this kind of approach. So the case study. This is the pipeline that we have, essentially. First, you have model training, post-processing, evaluation. This remains the same. But the mindset we are bringing to this approach is slightly different now. Okay. The case study is essentially, the task is to design personalized visual arts recommendation for the National Gallery of London. Have you ever been to the National Gallery of London, to the museum? Okay, so our task is you have a visitor coming to the museum, and you want to design a recommender system for these new users. A quick disclaimer before I move forward. Most of the, why is it flickering? Okay, there is some sort of delay. A quick disclaimer, most of the images and the plots that you are going to see belong to Cross-Cult Knowledge Base. It was a project, EU-funded project, which was done in 2020. So just disclaimer, most of the things belong to this Cross-Cult Knowledge Base. Yeah, so in the National Gallery of London, we have a huge venue, which is 3 floors and spread across 46,000 square feet. And then we have a set of paintings, around 2,300 paintings from mid-13th century to 1900. Now you want to design a recommender system for visitors coming to this venue. It's a huge venue spread across 3 floors. So the first thing is, the task is to design a recommender system, which is personalized. You have visual art, paintings, and you have a target user. Usually these are new users, so you have to make some kind of assumption based on anything you can find your hands on about their preference towards visual arts. So yeah, let's look at this data set. This is a sample painting from the National Gallery of London. You have the actual image of the paintings. You have some metadata information, and there is kind of semantically rich textual description about what is depicted in the paintings. So this is your input data. You have 2,368 of the same kind of data sets, samples. Now you want to build personalized visual art recommendation for new visitors. So right off the bat, you have a new user. You have no information about the user. You're met with the cold start problem. So in literature, there are like different kinds of preference elicitation techniques that you have to employ so that you learn a little bit of information about the user so that you can offer. For example, you can ask them to play with some rating games so that you get what they like, kind of sense of what they might like or what they might not like. So you do this, and then you get some kind of preference information. Now you have some information about the user. You have good information, let's say, about the data set, which is the painting. Then what do you need? You need pretty much a model. But before that, what is the task? So if you have a user who likes this painting, I give it a 5-star rating. Your task is essentially finding those paintings that are similar to this painting. Because the user likes this one, I want to find him all the other paintings that are similar. That is like the straightforward approach to generating a recommender system. But how do you find these similar paintings? What does similarity actually mean for a painting? So to do this, you need a model which kind of learns this notion of similarity or relatedness across the data set. Essentially, then you have a similarity matrix from which you can rank and generate recommender systems, recommendations. But now, what do we have? How can we find this model? So you have your image, the metadata, and you have some textual description as an input to your model. But now your goal is to find this model which captures this notion of similarity. But you need some kind of representation through this model. But what is a good representation in this case? What does a good representation entail? Let's see an example. You see this image of a dog. So what is a good representation for this image? If I give you this word dog, does it represent this image? It does. It pretty much summarizes this pixels into 3-word text. It kind of concises this. If you look at the image only without the representation, can you answer the question, is this dog mine? I can answer looking at the image because this is my dog. His name is Buddy. But if you look at the representation only, which is a dog, can you answer this question? We can't. So this gives us an idea of what kind of representation we want from the data. So what is the dog doing? Can I answer this? Looking at the image, I can, but looking at the text, I cannot. So is this dog safe? What is the dog doing? So there is some kind of action the dog is doing in the image, which you can only infer by looking at the image. So there is some kind of information loss when we try to represent the image, right? So this gives us an idea what kind of representation we want to drive from the data. So we want the description or the representation to be a bit more descriptive, yet still a summary of the image. So what if I say, this is a German Shepherd dog resting on a floor in a living room? Now we can answer a bit more questions, right? What is the dog doing? He is resting. What kind of dog it is? It's a German Shepherd. So you kind of have a better representation here. So essentially, a representation is a summary of data which is minimal, which omits unnecessary details and preserves important details. So for example, when you think about this with computers, they get numbers. And this is quite high dimensional. And it's going to be like an array of metrics where each dimension could mean different things. For example, the first dimension could embed some notion of color, maybe shape, size, different semantic components, right? So the idea is we want to have a good representation. And if we look at how this kind of evolved from the traditional machine learning, at the very early stages, people were trying to basically learn a classifier directly from the input data, which is quite high dimensional. And it didn't really work. And this is because we have very high dimensional. There is a lot of redundancy in the input, so the model, we cannot really learn a classifier from this to solve this task. This was a very challenging task for many years. And the problem is, okay, you have too much redundancy, and people eventually started to propose something called summarizing relevant information, or which led to the modern day, what we know, dimensionality reduction. So now we want to extract what we think is important feature from the actual raw data, and then learn a classifier on top of that, which kind of worked better, but it didn't really nail the task. And then with the evolution of coming deep learning or neural networks, now we no longer need to work with predefined set of features. Essentially, whatever is meaningful, the model will summarize and extract that feature for us. So whatever is relevant from this raw data, whatever feature is meaningful, the model can directly extract and summarize those features for us, which was great, and we started achieving superhuman performance. This was good, but then we started to ask other questions like, okay, we can learn features that are useful not only for specific tasks, but can we do more with these features that we learn using these extracted features? So essentially what this question is, you have a deep learning model, it extracts features, and then you want to engage several tasks with this embedding or with this representation. Sometimes we don't even know in advance what kind of task we want to solve. We just want to learn a representation which kind of is more powerful and generally useful for a wide range of tasks. So for example, you just, okay, can classify cats and dogs, but can I answer from this representation, are the dog healthy? So you can answer this kind of questions from good representations. And this kind of opened to the modern day representation learning. There is a whole other research domain. If you know, iClear is all about representation learning, and researchers try to come up with different kind of objective functions which kind of encourage this kind of properties to emerge when you try to design your model to extract features. So yeah, now what a good representation entails is essentially, first, we want it to be low dimensional. We want it to be a summary of our input data, and we want it to be reusable across different tasks. And also, we want it to be smooth and spatially coherent. This essentially means as you are searching this space for search and retrieval, you want to have a smooth transition between items that are semantically closer or related. And there are also quite a few things, for example, to be disentangled. We want it to be disentangled in a sense. For example, if you modify some element in some dimension, you don't want to affect, for example, the second row is, or in the matrix, you have embedding about color. If you change that, you don't want it to actually affect the shape of the content that is embedded. So these are, and also, of course, we want it to be hierarchical and meaningful. So these are like the kind of properties that we want when we try to find representations. Now let's come back to art recommendation. So we have a set of paintings, and we want to learn a good representation which kind of captures the semantics that is within the art. So before, the earlier approach were essentially using metadata. So for example, authorship, history, the size, the material used, different metadata information. So if you like paintings by Da Vinci, I give you a recommendation of all the paintings that were done by Da Vinci. Does it really capture? It didn't really work that well. Then eventually people start to use deep learning models. So we train a model that can learn visual features from the paintings. Now we use pre-trained models like ResNet, AlexNet, GoogleNet, or whatever we want, and then we use this to extract features. How? Using something we call transfer learning. So this concept of transfer learning is like very simple. So let's think about this as you want a model, and you have a huge data, and you want to learn the features that can achieve super performance. You want to find a good result. So your model has a good understanding of your huge data set. Now you have a new problem, let's say. First was classification, and then the second is basically detecting if the dog is sick or not. Now, but you have only, let's say, 100 images. You have a small data set, but you want to achieve good performance. So transfer learning is essentially transferring the knowledge that was learned through another model and then apply that to a small data set or small set of problems so that you can achieve a very good performance. The most straightforward to think about this is a kid trying to learn, for example, the alphabet, and then transferring that knowledge to actually read a newspaper. That's pretty much what transfer learning is. without going too much into the technical details, here I have an example of a VGG16 architecture. So what happens here is the first part, as an input, VGG16 is already trained on ImageNet dataset, which is like more than 1 million images. So it has learned general features about images from the internet. And you have this part, which we call a convolutional base, where the learning happens. And then you have a fully connected base. So what we do is essentially we keep this and then we reject the fully connected part. Why? So here in this case, for example, the general feature learning happens in the convolutional base. So that's what we want to capture. We want to retain or transfer this knowledge about general knowledge about images. But then we don't want ImageNet features at the end. What we want is features that are very specific to the visual art. So we replace the fully connected part with our own layers. So that's pretty much what you do when you use transfer learning. So we use transfer learning for learning features from paintings. So as a feature extractor. So basically we have all kinds of pre-trained image models. We use them as feature extractors. So you have a huge knowledge learned through pre-trained tasks. And then we want to transfer this knowledge so that we can have better prediction on a specific small task. So in this case, we have around 2,000 paintings, which is not a lot. So basically, we replace the fully connected layers with your own task, and you can achieve some kind of performance. So you extract features, basically. These features kind of capture what is embedded in the art. And you can use them basically to get a vector representation. So what this means is essentially you have similar paintings placed close to one another in this embedding space so that you can compute some kind of distance and then get some kind of similarity matrix to generate a recommendation. So visually similar paintings, ideally, if your model is good, if this representation is good, will be placed close to one another. So what is the problem with this? So in the context of art recommendation, okay, visual features are not really interpretable. You cannot really tell me what this is by just looking at the features. And you cannot explain to the user, why do you think these paintings are similar? If you use this to generate recommendation, you cannot tell the user why visually they have the same feature, but you cannot really explain it. And the other issue is the semantics. So when you look at this painting, what kind of emotional reflections are triggered in your brain? It's very subjective for everyone, which is beyond the visual aesthetics of the art content. So capturing this complexity that is embedded in visual art is quite challenging. So these models, while they are really good, but they kind of fall short in achieving this, capturing this nature of semantics in visual arts. So what can we do? This is also the issue. So what can we do? We need to go back to the data set. Then we have features, other features, like textual descriptions of the paintings, right? Which is semantically rich. So when I look at the image, there is some kind of reflection that is triggered in me, and there is some kind of understanding that I get from the visual aesthetics. But when I read out the textual description, I learn a bit more about what is the curator actually, the artist trying to communicate. And if you read the reviews about these paintings, you learn more what people actually associate this painting towards a certain themes or concepts. So there is some more semantics in the textual description. So what can we do? We can use this information from books, reviews, or textual descriptions to learn some kind of representation again. So the notion is the same. We want to learn representation. Earlier, we learned some kind of representation using the visual features, using transfer learning. Now we want to learn some representation from textual description. But these representations are kind of hidden, right? We cannot really tell from the image. So this is kind of latent, hidden, with what we call hidden semantic representation learning. So these are like techniques to learn this hidden concept. So now we have an image, and we have a corresponding textual description for each of these images. And we do basically topic modeling. So topic modeling is essentially tools or techniques to basically learn hidden themes topics. It's very powerful and popular in document retrieval or in NLP world. One of the most famous approaches for topic modeling is called latent rich allocation, or LDA. So you can think of this as some kind of black box model, which takes as an input some kind of text corpora, and then you get as an output three things. First, you get some kind of cluster of words, where each cluster kind of defines a topic. For example, it could be religion, it could be culture, and within each cluster, with each word has a certain frequency. For example, the word Christ could have more frequency in the topic religion, right? And you could have different frequencies. And then, of course, from this you get, for each document, there are different proportions of topics within each document. So LDA is essentially, that's what topic modeling is essentially doing. So if you Google LDA, or if you try to look at the architecture of latent rich allocation, you will find something called LDA plate diagram, which is not quite intuitive to understand. So let's look at the components of what this architecture looks like. So we have M number of documents. In our case, we have a document exactly the same number of the paintings, so around 2,300 paintings. And then in each document, you have N number of words, which we want to put as an input to this black box model. And then we want to get some kind of cluster of K topics, right? And then from these topics, we get some kind of distribution or frequency. For example, word A can have 0.7 frequency in a certain topic. And then when you do this, you get a kind of another distribution over each document. So per word, per topic distribution, and topic per document distribution. So, and also we have additional two alpha and beta concentration parameter, which kind of inject some domain expert knowledge. So these are like basically what you will find when you look at the plate diagram. Okay, so what happens is essentially LDA is kind of, when we unpack what happens inside, it's kind of an iterative algorithm. You start with initializing the parameters, and then you iterate, resample for each topic. You assign a topic for each word, and then you resample. So basically what happens is, let's say, for example, you have a document, and then you have the dots depicting some kind of word within that document. So the colors represent basically topics. So I assign topic green, topic white, red, and then everything. And once you're done, in the next iteration, you come back, you look at, okay, the first distribution is theta psi distribution, temporary distributions, right? And then what LDA does is essentially come back in the next iteration, you look at what you assigned. For example, the first word was assigned to a topic green. But when you look at it, topic green is not really a topic that appears most frequently in this document. So it kind of resamples. So this kind of sampling is not random. Actually, it follows Dirichlet distribution. And then essentially it tries to answer which topics occur in this document and which topics like this word. I won't go too much into the details, but I just want to emphasize, we will see that in the lab later on, how this all unfolds when you try to actually build a topic model from textual descriptions of paintings. But LDA, or the topic model, actually asks you to define how many number of topics do you want. You as an expert have to define the number of topics, and there are different sampling strategies. For example, Gibbs sampling can be used to, and also there is a measure called coherence to detect like what is a good number of size of or number of topics you have to decide. And then you unpack, you look at the kind of distribution of words that are existing within each document. So there are some limitations, but it works. So there is this GenSem library that we are going to use later on to actually train a topic model from the painting distribution. And if you're interested in the Dirichlet process, you can even also check out this link, a very nicely documented description about Dirichlet process. So now what we want to do is, you have a painting. For each painting, you have a corresponding textual description, which is a document, and then you want to feed to LDA, and then what you get is a distribution per each document, per topic distribution. This is essentially a vector where the number of columns is essentially the number of topics you want to decide. So if you want to have 10 topics, you have 10. And then this is basically a matrix and an embedding space. And then you can use this to create a similarity matrix, just like we did with the image-based or transfer learning using ResNet or VG16, and then you have your recommendation. So you have a model that kind of captures what is embedded in the topic. So for example, a textual description of this painting can have 20% religion, 30% culture, and maybe some other topic. So if there are two paintings that have high proportion of the same concept, these paintings could potentially be similar, semantically speaking. So we can use or leverage these kind of representations to drive this missing semantic component from actually the visual elements. Okay, so you have a pre-trained model like transformer-based approach, also SBERT, doing exactly the same thing. So these are different approaches for topic modeling. So I will quickly zap through this, and we end up with this. So we used LDA and sentence BERT and then ResNet. All of them are kind of extracting a feature, learning some kind of representation from raw input data. And then you end up having some embedding space from which you can transform to a similarity matrix. So again, the idea is quite simple and straightforward. You want to have some kind of embedding which captures similarity, so that similar paintings are clustered together. Okay, let's come back to this pipeline. So now we trained the model, right? We did all those kinds of fancy machine learning stuff, and we built a model. And now it's recommendation time. Now you want to give this to the user, right? And what do you want to do when you do that? The user likes a certain painting. So I tell you, I like these paintings, 3-star, 2-star, whatever kind of rating. And you want to expand this into the active user preference into the similarity matrix. So this is very straightforward. You basically want to score the entire data set based on this. So these weights kind of bias the similarity matrix so that you can re-rank. And you have this weighted average distance calculation based on which model is trying to give you. So you can generate recommendation, right? Now comes evaluation. Okay. Now let's talk about evaluation. So what do we want to evaluate here? Do we want to learn how good is the recommendation, or do we want to learn how good are the topics in this case, or what do you want to evaluate? Ideally, you want to satisfy the visitors. You want to give them some recommendation that they might enjoy based on their preference. So there are like different approaches for evaluation, which is motivated by common approach in machine learning or information retrieval. So you have to do offline evaluation. In this case, you just have to use offline measures. There are no users involved. It's very cheap to do, and this is what almost any RecSys researcher, including myself, have been doing for many years. So the first to-go approach is is there an open source data set that I can use to actually measure the performance? And then a little bit expensive approach is to actually conduct a user study. You have to recruit participants to your study. You design a model, a RecSys model, give the recommendation, and then ask them questions. Qualitative, could be quantitative. How good is the recommendation? What is your perception? You learn some information from that. And then in online evaluation is the most expensive, but it's trustworthy. You deploy the system to users that are not aware of this experiment you are conducting. Could also be very catastrophic. So a couple of basic design guidelines when you evaluate models or RecSys. Can you accept? First thing is forming a hypothesis. So you have to form concise, per se, restricted hypothesis. What do you want to evaluate? Do you want to measure how good is your recommendation, meaning algorithm A better predicts rating of the user better than algorithm B, then you measure accuracy. If you want to know how diverse the recommendations are, you can measure diversity. So you have to be restrictive and concise based on what you want to assess in your evaluation. Another thing is controlling variables. So variables that you are not actually testing should remain fixed. So for example, now we have algorithm A predicts a rating better than algorithm B. But You want to measure predictive accuracy, right? But if you train the first algorithm on a data set from the National Gallery, and then you train the other algorithm from another museum, you have a problem. You cannot really tell why algorithm A is better than algorithm B. So what do? You have to train both on the same data set. Yeah, so the first approach to evaluation, which is offline, is essentially, as I said earlier, based on offline or assumptions of users, that users will behave the same way, right? You have maybe real, maybe fake users in your data set that give some kind of rating, and then you assume when I deploy this model, users will behave the same way, which could not be the case because time changes, people change. I liked a certain content today, maybe tomorrow for some reason I'm no longer interested in some content. So this cannot really reflect what you would anticipate, but it's the best thing you can do as a starters. So first you have to evaluate offline to help you make some reliable decision before you move forward with whatever kind of recommender system. It's easy, and that's why most of us do it first. And the downside, as I said, is you cannot really measure the influence of your RecSys on the actual users. But it's good for adjusting some hyperparameters. For example, if you want to adjust like the topics, you can use coherence or whatever kind of metric, and you can retrain and fine-tune your model. It's good, but it doesn't really tell how it influenced the users in real life. So when you move to a user study after doing an offline study, or maybe directly to a user study, you have to recruit participants. That means as an academic researcher, this can also be challenging because you have to pay the participants, right? And you ask them questions, and then you observe the behavior of the users. So it could be qualitative or quantitative. Do they like the user interface? Should I change the interface? You might have a great model that does a good prediction, but if you deliver it in a very bad user interface, it could significantly affect how users perceive your recommendation. So these kind of things that you can learn and adjust and adapt through a user study. It's great, but also user studies have some downsides. Of course, it can be expensive to conduct depending on how much budget you're willing to spend. And of course, users usually are motivated by different things, especially when you recruit participants. If you use crowdsourcing platforms like Prolific or Mechanical Turk, there are different motivations for the users to participate in your study. They just come here to collect the money, or they are just honestly trying to evaluate the RecSys that you developed. So common practice is to safeguard against this. Maybe you introduce some quiz. You can ask 100% approval rate, for example. And maybe, for example, in our case, we put some requirements like they have to have hobby art in their profile, for example. So you can find kind of the right stakeholders, but there is only so much you can do. Most of it is out of your control, but this is the best first step you can do. And also, yeah, finding subjects, like I said, finding subjects that are representative of what you want to evaluate. For example, for our case, we want to evaluate recommendation of art. So ideally, we want museum visitors, people who actually go to a museum to interact with this kind of tools. You don't want users that have no interest in art to evaluate these RecSys because it doesn't really make sense to learn something from their interaction. So yeah, ideally, because it's expensive, you have to do pilot tests to make sure everything is working. After you pay the participants, it can happen. Your system is overloaded. For example, the common issue is like stress test. So you have to do stress tests. So for example, when you deploy a study on Prolific and invite 1,000 users at the same time, and if your server cannot handle that, your system will crash, and you have to pay 1,000 users for collecting literally nothing. So you have to like stress test and like these minor things, but will save you a lot along the line. So yeah, there are a couple of approaches to conduct user studies, for example. So the first is between subject and within subject. So these are like two important differences. So in the first case, you have between subject, and In the second case, you have within subject. So the difference is essentially you recruit participants, right? And then you split the users. So you design a RecSys engine A, and then you expose the first group to the first engine, and then the second group to the second engine. But within the within subject case, first they interact with the first engine. Once they are done, they go to the second engine. Here, it's beneficial because it's more informative. They can compare the performance of the two models, right? There is learning across different tasks. But in the first case, you cannot really compare. You cannot ask them comparative questions because one have not exposed to the other. But it's good to actually conduct some longitudinal influences or long-term effects of these engines on the user. So depending on the task, depending on the kind of observation or evaluation you want to accomplish, you can employ either of the two. Yeah, and this is done with a set of users. The last one, which is the most expensive and reliable approach, online evaluation. So you design a model, you deploy it with real users, but you don't actually tell them you are conducting experiments. So you are a user, for example, of Amazon, right? You want to purchase something. Maybe Amazon is testing some product recommendation service that you are not aware of. So you behave in a certain way, and they learn something. It could be catastrophic. Maybe they are giving you really bad recommendation. You'll be like, no, I'm not going to use this platform again. I will try to find other e-commerce websites, which could be a catastrophic loss for the company. So there are a lot of consequences that this could bring, but it's very good to learn actually how the users behave when you actually deploy the platform in real life. Yeah, so these are like 3 approaches that you can use to evaluate, but ideally, it's better to start from the offline than do user studies, and if you can afford, go to the actual deployment of the systems to avoid this kind of effects. Yeah, even after a careful evaluation of this, RecSys could still fail because we are, again, in a cyber, physical, and social systems. One feature is evolution of this system. It's not stable. It's changing constantly. You are being influenced by other users regarding your preferences, your interests. You are changing, adapting. So what I think you know or what I think you like may not actually be true by the time I deploy the model. Maybe you have evolved from those preferences and the model is no longer viable at this point. So yeah, we have to think about this. Now let's come back to our art recommender system. So we build a model, we extracted features, and we end up with 3 different representation space. So this is like an embedding space of the National Gallery dataset. So they look quite different, all of them. Which one is the best recommendation? So if I find a painting from the first, and then I want to generate recommendation using all of this, I get different set of recommendations, and which one is actually good? According to the offline evaluations, maybe all of them could give you like great performance, but when you deploy, you don't know how. So you have to conduct actually a user study to actually learn what the users actually perceive. So we end up testing against 3 different recommendation pipelines. So if you click that link in the PDF, it will take you to the actual platform that we used. It looks something like this if you log in mobile and interface. So what we actually measured is how good is the recommendation, essentially. The go-to approach is how accurate are the recommendations based on the preference or the rating that you gave me, right? That's what we normally evaluate. But these beyond accuracy measures, for example, diversity. How diverse are the recommendations? And the notion of serendipity. How surprising, the element of surprise. So, and also, how is the learning? Meaning, like, I found surprisingly interesting paintings. So when you think about it, if you can manage to strike a perfect balance across all these evaluation pipelines, the accuracy is good. You are giving diverse paintings, meaning the user is learning something new that they have never seen before, which they might end up liking, or maybe not. So this beyond accuracy measures kind of gives us an idea of what kind of influences that we want to put on the user when we actually serve a recommendation. So these are some of the findings that we have in our user study. And if you look at closely, LDA was performing much better in most cases. And then we have BERT worse performing, interestingly. Both are topic models. And we have ResNet kind of doing okay. So one takeaway from this is both visual and textual features have some element of semantics or relevance. And let's see what we learn. So for example, we have a target painting. So let's say a user likes this painting. And according to LDA, the most similar painting is this one. Do you agree? Or do you think this is a good recommendation? If you like the first one, and I give you a recommendation, what do you notice? Yeah, it's a portrait, something that looks like a Bible. And if you look at actually the topic models, then you can see that they have both similar distribution. And topic 8 actually kind of stands out in both cases. And if you go in the topic 8 and look at the words inside, you have Christ, Saint, Jesus, Evangelist, Cross. It's pretty much a religious context. And LDA is actually doing a pretty good job in capturing the semantics. And we actually, in the first study, we gave the users explanation as to why we are giving them recommendations through using like word clouds. So for example, because these two paintings, you like this painting, it contains this kind of concepts, and we think you might like this because it's also the same notion in terms of the semantics of the topics, which is known to actually help users understand why you are giving them the recommendation, which they appreciate. But if you look at the other two, for example, BERT also is doing a good job in terms of topic modeling. So you can see the same topic distribution. Visually, the two paintings, they look similar. And if you unpack the most prominent topics, you can see similarities. But if you look at ResNet, the most similar recommendation for the first one, let's take a closer look here. What do you think? They look visually the same, right? There is some visual element like red dress, a woman standing, and there is some winged figure. There is visually appealing component, but we cannot explain the visual features to the user. What we can do is we can go back to the documentation of the National Gallery and look at actually what these paintings are talking about. So the first painting, Time Orders Old Age to Destroy Beauty. It was by Bantoni from 18th century. But the second painting is The Donor from the 16th century. Now, the first painting, the winged figure below depicts time. The old lady depicts old age, and the woman depicts beauty. And in this painting, from the documentation, Bantoni is actually trying to encourage considering the brevity of years and the inevitable passing of time. But the second painting, this is Mary Magdalene. And this is a precious ointment. And this is actually a religious painting. It's found in the altarpiece of a church. So if a user likes this painting or interested in religious content, the first painting might not be actually a best or recommendation, because clearly there is a semantic gap. To begin with, they are not from the same time period. So there is a semantic gap, clearly. And yeah, now we know each engine has different levels of exposition for capturing actually this hidden semantics. So why don't we combine them? So the first thing we did was using rank fusion, reciprocal rank fusion, which is basically use pre-trained models separately and then fuse the recommendations together. So you can basically decide what percentage of the recommendations are coming from each engine. You can do it in that fashion and then see what works best. Maybe in some cases, 75% of the semantics is captured by the textual description and the remaining can be captured from the visual component, but we are actually ranking or fusing rankings. We are not actually capturing these embedded features together. And then we did another user study. Interestingly, now we learn some kind of pattern, some interesting pattern emerged. If you look closely, LDA and BERT, when combined, they actually perform better across all beyond accuracy measures. in terms of accuracy, in terms of diversity, novelty, serendipity. So the takeaway here is essentially hidden semantics that are embedded within visual arts can actually be captured through the fusion of the two modalities, the image and the visual component. So what can we do? Now we know the fusion actually delivers better recommendation, but we are not actually fusing. We are just combining rankings. Can we learn them jointly? And the next approach was actually to learn a joint embedding space for both of these recommendation tasks. Okay. Yeah, so this is the two models that we propose. So if you're familiar with clip and blip, are you familiar with blip and clip? So these are like multimodal representation learning techniques. So in the first case, we use contrastive learning to jointly learn a joint embedding space from visual and textual. So but at the end, we are going to have a joint embedding space for both visual and textual. The same with blip. And we run another user study, of course. Now we have blip outperforming clip. And we have late partial and late total. This is essentially the reciprocal ranking fusion. Late partial and late total is like fusing everything together and then re-ranking. And in all cases, we see that the multimodal engine blip was actually doing a good job across all these evaluation pipelines. So yeah, now we did all the fancy modeling of the data set. We generate recommendations, and then we kind of saw how this evolves in the user's experience in terms of beyond accuracy measures. But this is like just a small piece of the puzzle. The task is to design a recommendation and guidance for a museum visitor, right? You give them what they like, but then you have to actually deliver it. That means you have to guide them in the physical museum, which is 46,000 square feet across 3 different floors, which brings more components, more stakeholders to the place. So now you have a good model which captures good representation of the input data. But can you actually use this and then take into account the surrounding the user is actually evolving in? There is a crowd tolerance. Users they don't like to walk too much, so they want to find all the paintings close to a certain. Some people don't mind to actually walk in a museum too much to actually find stuff that they really like. So all these come into play, and then you are driving a single recommendation to the user. In some cases, there are museum experts. They also want to influence the recommendation. They want to educate visitors about some stuff. So this brings the notion of multi-stakeholder awareness to actually drive recommendation. It's a multi-level problem. You have a content recommendation on one hand, and you have actually a path recommendation on another hand. So yeah, I mean, I think we can take a break now, 10:32. Right? This is a coffee break, if I'm not mistaken. So when we come back, maybe after half an hour, we see the multi-stakeholder notion and then go back to the CPSS paradigm and see how we can actually use a framework to model smart interactive environments for personalization tasks. Okay, let's start. So again, we come back to this typical RecSys pipeline, and now we're talking about multi-stakeholder awareness. So let's come back to the case study. Designing visual art recommender system for the National Gallery or for, it could be any museum. But now we have slightly more things to think about, not just items or features or embeddings. We have more things in the physical space, and we need to really model the context to understand what is happening in the museum. Why is this important? Because usually if your recommender system is not that great, not in terms of modeling, but in terms of actually delivering the recommendations, you end up with situations like this, which is not pleasant for nobody, not for the museum, not for the users. So how do we avoid this? We have great state-of-the-art performing models to generate recommendations, but how can you actually deliver this so that users have a seamless experience in the museum? That's the challenge. So there are a number of stakeholders here. It's not just the user you are dealing with. So museums can be seen as a cyber, physical, and social systems, as we were talking about earlier. Why? Because, okay, we have points of interest that you want to personalize, recommend, and you have visitors, you have smart devices with some sort of social capabilities, let's say personalization, and you have also some devices with no social component per se, and they exist together in the same physical space, which is typical definition of cyber physical social system. There is a systemic notion of modeling that we can employ here. So to do this, first we need to model some recommendation and then deliver it through mobile guide or whatever kind of delivery medium that you plan. It could be mixed reality glass, it could be a mobile guide, or if it's even a tablet. Regardless, we need to model the context or the environment in which the user is evolving. Coming back to this evolution of cyber physical social systems, so we are here, right? We are humans interacting. We have a system where humans interact with this socially constrained, which we want to make them socially capable, whether it's a mobile or a tablet or a glass. We want to implement personalized recommendation through this, and this is the interaction we want to model. And yeah, so this social component is essentially embedded through personalization, in this case through a recommendation algorithm, to help the devices be a good companion for the visitor in the museum, right? So the CPSS paradigm or notion takes this systemic view of modeling entities. Can you admit? Okay. So you can view the whole world as a gigantic cyber physical social system. And within this huge system of systems, we have subsystems that are themselves system of systems. So let's talk about the museum, which is kind of a smart environment, let's call it INV. And this is kind of a subsystem of the big cyber physical social system, where inside we have these circles denote entities. It could be a user, it could be a device, it could be anything that has interaction capability. So users, devices, they are all systems within this system of systems. So ideally, we say personalization is a function of a social component, right? Either it's implemented through RecSys, it's a function of a social component to help visitors have a seamless experience. So if you think about one system, for example, with some kind of social component, think about a human and another human, a human guide, for example. And there is another human. Both have some kind of social component, so there is a social interaction. And if one is a device instead of a human, we want to ensure same level of kind of interaction experience for the user, right? So let's say the personalizer, the first system that kind of helps the other system to have a seamless experience, in this case gives recommendations, suggestions, paths, optimization, whatever, and the other system becomes the user. So it could be a human, it could be a device, but everything is a system. The device has its own components, its own objectives, different constraints. It's a system, basically. And there is another system interacting with another system. And another modeling aspect that we can take is a crowd. So these two entities, two systems interacting, they are not alone. There are other systems, there are other users, there are other devices in the same physical space interacting with these users that have a direct or indirect influence, right? So we model the crowd as systems that have direct impact on the user. For example, a crowd. So you might have a different tolerance to crowds in the same physical space. So they are influencing you. Or there can be other systems in the same physical space influencing the user or the personalization task indirectly. For example, visitors that went to the museum before you, they can leave a review, and you read that review, oh, this painting is really interesting, and they wrote something, you read that. You are somehow influenced by their observation. So they're not directly in the same physical space as you, but they are kind of influencing you. So now one system is trying to implement personalization or recommendation for another system, which is a human in this case, and you want to take into account all these components. And this essentially can be formulated, leads to formulate this task of personalization in CPSS context as a function of the user, the personalizer, the crowd, and you can have context elements depending on the scenario you want to model, and the environment itself. For example, the museum itself has its own objective. It's a system. There is a rule. There is a goal that the museum wants to achieve. So you have to satisfy or respect that when you are designing personalized recommendation for the users. So the analogy of CPSS is really powerful in this case. You can try to abstract interesting concepts or components, systems that have an impact on the user and on the personalization tasks that you want to model, and abstract everything else and actually deliver personalization. So it kind of helps you to visualize and identify what is relevant in this case in the context. So, for example, in the museum context, this formulation can be easily adapted. So your user becomes your visitor, and the personalizer could be a mobile guide. You have a crowd of other visitors in the same physical space, and the smart environment in this case is a museum. And depending on the context you want to model, the day, the time, the theme, or whatever kind of scenario that you are trying to deliver a personalization, you can simply adapt this formulation as a function of the visitor, the mobile guide, the crowd of other visitors, and the exhibition area itself as an independent system. Why is this interesting? Because now you have identified or abstracted out all important components. And then you can dive deep into each component and what is their role in the implementation of personalization or in the user, on the user, basically when they interact. Let's look at these three components, for example. The mobile guide is, let's say, the algorithm or the personalization system that you want to implement. And there are visitors, there are a crowd of visitors, and the exhibition area or the museum itself as an independent system. And what do they entail? Let's look at the visitor. The visitor himself or herself have preferences, interests. They have a limited availability. You go to a museum maybe for 1 hour. So you need to find paintings that you can visit within 1 hour. So you have to round the list, and you have a different tolerance. You don't want to visit a room which is crowded, so your recommender system should help you to navigate smoothly in the museum, which is sometimes not easy to do. And visitors also tend to have different visiting style. And there is this interesting animal metaphor for modeling museum visitors. I think you might find yourself in one of these categories. You could be either an ant, butterfly, fish, or grasshopper. So the ant visitors are a kind of visitor that actually spend long time observing all exhibits. They don't have really clear preference. They move close to walls. And the fish visitor is kind of visitor who walks mostly through empty space. This is you, maybe. And a few stops here and there, just to glance at some interesting, and then if you don't like it, and then you carry on. And you have this grasshopper visitor who's very specific at what they want. They know what they want, so they jump from one room to another room, and they spend long time observing specific exhibits because they know that's interesting for them. They take time reflecting on these exhibits. And the fourth one is the butterfly, which frequently changes direction and usually avoids empty space. So this kind of analogy is quite useful when you try to estimate visiting time. So you can have a tool which helps you around the list of recommendations that you can estimate given the available time of the visitors. And of course, visitors have fatigue, disability, age, a lot of things that you can consider that have value in the physical space. And the second component, the exhibition area or the curator, also have their own preference as to what kind of recommendations they want the engine, the RecSys system, to deliver to the users. They have opening hours. So if you generate recommendation of 1,000 paintings and the user is there just for 1 hour, he cannot actually cover this route. So it's infeasible. So you have to respect this. And also, there are crowd capacity that a certain venue can actually accommodate. So if you lead everyone to the same venue at the same time, you end up with the Mona Lisa situation where you have everyone looking at the same painting, and you don't want to do that. And the crowds, like I said earlier, other visitors, they could have their own different preferences, their ratings, which could in turn have some influence also on the popularity of a certain paintings. So some paintings become quite famous and popular because of how the public perceives them. And this might affect a new user. So you heard about Mona Lisa, and then when you go to Louvre, you always want to see Mona Lisa. And if the user is actually in the physical space, and then there is another challenge it brings, the crowd congestion. So you want to avoid that. So all of this is while you design a recommendation for one user, but you have to take into account all of these components. So we also have this curator-visitor trade-off because in museums, sometimes they organize exhibits by team. So today, for example, they want to expose visitors about religious paintings from the 13th century. So they want the recommender system to guide visitors to this kind of content, but the visitor is not interested in religious context. So you have this dilemma where, what do I do? Should I satisfy the visitor? Should I satisfy the curator? So essentially, you end up with a personalization task where you have to make the best possible compromise in the end. You are delivering one single recommendation to a user, one user. But you have to take into account a lot of different stakeholders' perspective to the design of this. And this is essentially an optimization problem, which is constrained multi-objective optimization. So now you kind of get the idea. So you have a clear picture of what you want to do, and you have all the pieces in place, but then how do you bring them together? Comes then the modeling task. So we approach this problem in two levels. So the first is, like we saw in the second session, it's the point of interest recommendation challenge. You have to have a good model that captures a good representation to drive valuable recommendations. And you have to use this model and then deliver it in the physical space. You have to guide the visitor, respecting all of these components from the physical space. So coming back to this RecSys pipeline, now we kind of have an idea of what we want to do. The task is the same, personalization. But now the components are different. It's no longer just matching similar paintings, but it's rather thinking about how do I make the best possible compromise? What is valuable? The problem is always the same. There is a new user. You have to model some kind of preference elicitation and then build some kind of profile. Then you move on. You do the topic modeling or the representation learning through whatever kind of fancy machine learning you do. And then you end up with this similarity matrix. OK, you grab a good representation. You get this. Now you end up with a profile which looks slightly different than the classic case. Now you have a new visitor. You interact with the visitor. You get some preferences, ratings. But then you also ask the visitor, how much time are you willing to spend today? 1 hour, 2 hours, 30 minutes? Then what kind of visiting style does the user have? So it can help you to estimate the amount of time the user spends per exhibit. So you can kind of round the list. And then there is this crowd tolerance. Are you interested in visiting crowded venues if there is a painting that you really like? Or you really want to avoid this? So somehow try to quantify this information. And of course, some users don't want to visit popular paintings. You have some kind of tolerance to see popular paintings or items in your recommendation list. And fatigue tolerance is also another thing that you consider. Are you willing to walk, like, let's say, 5 minutes to find interesting painting, or you prefer to find all the recommendations in the same area? Remember, we have 46,000 square feet of museum across 3 floors. So this matters a lot. And if the user is also disabled, we need to have some accessible routes, which could drastically change the paths that you have to follow. And also diversity tolerance. So this is something that we want to measure to introduce a notion of learning and discovery, as we talked about recommendation evaluation earlier. The user-centric evaluation framework goes beyond accuracy. So when we introduce novel serendipitous recommendations, we are introducing to the user something that they never saw before, or something that is quite diverse from their profile, while still maintaining the accuracy. So we want to strike this good balance. So, but still, the user could have different tolerance. I want to learn something new, but not too much. You know, I want to learn maybe 1 or 2 new paintings, but still I want my recommendation to match my profile. Some users might be flexible. I want to learn something new completely, play with my preferences and give me something new. I want to learn something. So this is also some kind of tolerance value that you can collect from the visitors. And on the other hand, in the museum, you have the model of the items, opening hours, crowd capacity, story groups like themes that the museum experts want to expose. And there are also some rules that you have to respect when you guide the visitors. So you have to combine all of this and generate one list of recommendation and some paths that will take the visitor to navigate in the museum. So moving forward, we have this matching user preference, the first thing that we did earlier. What we did is essentially the first part. There is a visitor, you ask query, you build a preference model, use your pre-trained models, extract features, and then generate recommendation, then you have a score. Now there is this additional concept that we just introduced about popularity. So now we can get a list of items in the dataset based on their popularity. So how popular are these items within the museum? So you can get another score for every painting in the dataset. Then we need to somehow combine these scores. So what we did is essentially put this together, and then we ask this hyperparameter, which is a user-provided hyperparameter. How likely are you tolerating this kind of popularity in your recommendation set? So you combine this, and you can create some kind of an aggregate score which reflects the utility, the true utility of the recommendation for the user, plus their tolerance towards popularity. So now you have an aggregate score which kind of tries to capture this notion of popularity, which can be biased depending on the user's feedback. Okay, now the second component is the visitor, not the visitor, but the curator's experience. So the curator's goal here. For example, in the National Gallery dataset, you can find these story groups, which are curated by the artists, like women's lives, contemporary style and fashion, water. So all of these are story groups, meaning you can think of them as kind of baskets where a lot of paintings are put together. So what the museum curators want is, I want the recommender system to expose the visitors to at least 8 of these story groups. And if you look at this plot again, you can see that the distribution of these story groups. You can see majority of the paintings are uncategorized, but 8 of the story groups are quite few. So your recommendation set should actually select items from each of the story groups at least, which can be completely against with what the user wants to see. So you have to kind of find a way to model this curator's goal, which is exposing visitors to this set of content. So what we did is essentially we introduced a fair story selection function, which basically tries to optimize or maximize the selection of the stories across these groups. And it's easy to understand this way. So think of it as a basket. So let's say we have 3 story groups, the green, the purple, and the red. So if you select items 2 items from the first story group, 1 from the second, and 1 from the third, this function gives you higher value instead of selecting only all of them from only 1 story group, owing to the square root of this function. So when you apply this function to your selection strategy, what you get is essentially a recommendation set which maximally covers these story groups in the recommendation set. But this is only what the curator wants. And then this discussion leads us to different policies. So the first one is, of course, matching the user preference. You have some utility you want to maximize. And then you have a second goal, the curated story groups. So simple convex combination. We asked earlier the user, how likely are you interested to visit popular paintings? And then you can normalize that and use it as a user profile hyperparameter. The first half of the objective function is maximizing the utility towards the user. And the second half is kind of optimizing the utility for the curators. And it's still subject to some time constraints. So the visiting time should not exceed the available time of the visitor. And then we use this analogy of animalistic metaphors to actually estimate how much time would the user actually spend in each of these paintings. If you are like a grasshopper, maybe you spend 5 minutes per painting in your recommendation. Or if you are another kind of visitor, you can somehow use this to estimate the list of recommendations. OK, now you have a technique or an algorithm which gives you a list of recommendations and tries to actually make a compromise between all of these contents. OK, great, you have a list of recommendations. Now comes the paths recommendation. So we have the map of the National Gallery. We know where each painting is located in the museum. Now you have to guide the visitor to actually visit across this 46,000 square feet, across 3 different floors. OK. You project the scores of each painting in your recommendation set to the venues. So there are basically a path is a combination of rooms, right? A combination of venues. So you want the cheapest path, which is basically the sum of the scores of the rooms, which is essentially the sum of the scores of the paintings in each room. Are you following? Does that make sense? That's what you want to maximize when you optimize the path. And you have to respect the crowd size in each room. The visitor spends 20 minutes in this venue, and then in the next room, the crowd value is subject to change in real time. So you have to think about, OK, optimizing and make a decision. Would I change the path, or I will keep it the same? So if the threshold of the tolerance exceeds a certain value, you end up recomputing. So yeah, and then another interesting, while you're doing path recommendation, another interesting scenario is you could end up in a situation where the next venue could have the same score. So you have one room with a score of 10, let's say, but there is only one painting, which is very important because it has a score of 10. Maybe in the second room, you have a score of 10, but there are, like, let's say, 5 paintings with 2 score. Then comes the decision you have to make. Does the user value quality or quantity? If the user wants to visit most interesting paintings, but few, then you send him to the next venue with 1 painting. But if the user wants to see as many paintings as possible, then you have to decide. So we have a small function that does that variation between quantity and quality. So again, this discussion leads you to have 2 different policies here. First, you want to maximize the score of the relevance of a path, which is you want to maximize the score of a path, whether it's quality or quantity, depending on what the user wants. And you also want to minimize the travel distance. So here, we model the travel distance as the distance between the sum of the distances between 2 consecutive venues. Why? You can think of this as a traveling salesman problem. But the layout of the National Gallery sometimes forces you to come back to the same venue in order to traverse between the rooms. So TSP doesn't work here. So you have to come up with some way of quantifying this value. So that's what the distance, consecutive distance is doing here. And of course, subject to a set of constraints. And then we do a set of convex combination using this tolerance towards diversity, fatigue. So in this case, you want to maximize the score of a path, and you also want to minimize the travel distance. And you have this lambda parameter coming from the user. Are you tolerant to walking too much to get good recommendations or not? And it is subject to, of course, time and crowd tolerance. Very challenging. Sometimes you end up having an infeasible solution. So you have to compromise some things. But this is like the real problem that we have at hand. And if you really want to have a user-centric RecSys, which actually values the interaction between the users, the property of the user and the property of the RecSys and their interaction, you have to take into account all of these components. And yeah, this is what the app looks like. So the preference elicitation phase, you have like some games like, dislike to profile the visitors. And then in the end, you get recommendation, which takes into account popularity in the curator's team and still tries to be personalized. But you are no longer doing personalization now. You are departing from solely optimizing for the users, taking into account multiple preferences. And how does this actually affect the user? What does the user think of this kind of recommendation? Of course, you model everything, you try to model as much as possible, and then you end up with a recommendation set. But how does the user perceive this across these user-centric evaluation frameworks? You do a user study. And the first study on a Yilma paper 2021 we did was essentially to measure LDA, ResNet, and the CPSS approach is basically combining all of these things on the content recommendation level. So you can see the accuracy is kind of less than LDA. Still, LDA is the winner. But it did not really, adding all of these components in the recommendation pipeline, it did not actually cause a significant worsening in the performance of accuracy. But how does the user perceive it in terms of learning, in terms of discovery of new contents, surprising contents, diversity? And in all of these components beyond accuracy measures, actually putting all these components seems to work well in terms of users' perception. So striking this kind of balance across all beyond accuracy measures is the kind of human-centric recommendation that we want to have. And moving along, so what we saw is essentially understanding the context or the problem setting. We talked about a museum, but you can think of modeling a personalization task in a conference venue, for example. You can think of personalization in a factory, smart factory, production systems. Wherever you can think of a human interacting with a device and another human, which is a cyber-physical system, you want to give personalized recommendations, you don't just talk about preferences and interests. You need to take into account everything that is influencing the user and the personalization task. So the CPSS paradigm, although still debatable in terms of should we actually proceed towards designing a CPSS or put human-like components in devices or talk about general intelligence, is debatable. But the frameworks is very powerful and helps us to actually model any kind of personalization task and attempt to actually come up with some reasonable solution. So you have competing objectives, constraints, and you basically try to prioritize objectives. So some design guideline in general for a personalization task in CPSS kind of environment is basically composed of 3 components. So you have the environment itself, you have the user, and you have the method that you employ, the computational method that you want to use. So the CPSS or the systemic view helps you to model, identify important components, which can be beneficial to model effectively the context and then decide where, for example, if you are giving an art recommendation for an online platform, you don't have all this problem of crowd, all of that. So if you effectively model the surrounding where the user is actually evolving, you can decide, do I do pure personalization or should I branch out and do multi-stakeholder awareness? This will help you to actually properly formulate the problem and then employ the right computational methods for the delivery of personalization. Which computational method works, and then you actually apply personalization. But this is a two-way street. Why? Because this is a dynamic environment continuously evolving and changing. So you have to monitor continuously and then adapt towards these changes. So this is like the key takeaway from this portion of the lecture. You always want to think about the environment, the user, and what works in terms of computational modeling. So now let's talk about some downstream applications. I was fortunate enough to actually work on this art recommendation and explore other downstream applications that could actually benefit from all of these models that we did for entertainment purpose. One is art therapy or visual art recommendation in the context of healthcare. So to give you a little bit of understanding as to the context, there is a condition called post-intensive care syndrome. So if you think about patients in an intensive care unit, the design of ICUs, or if you have ever been in an ICU, is often prioritized or focused on actually delivering medical activities, which often overlooks the mental or psychological impact of this environment on patients. And this is a collaboration research between University of Twente and us under the framework of Digital Nature project, just to give a quick disclaimer about the kind of research outputs. So you have patients in an intensive care unit, and once they are released from the intensive care unit, due to the traumatic experience they have, they could develop delirium or what we call post-intensive care syndrome. And this happens usually after they are discharged or released from the intensive care unit. And research shows that almost 80% of patients that are released from an intensive care unit suffer from this condition called PICS, or post-intensive care syndrome, which affects their mental condition significantly, but also has some physical and cognitive also impairments. And this is characterized by anxiety, depression, post-traumatic syndrome, which could be treated by psychotherapy, but it takes almost 1 to 2 years not to recover, but to start seeing significant improvements. But in research, there are like interesting evidences between nature exposure and healing, or positive destruction for psychological experiences. So research shows that there is a strong link between nature and mental well-being. And there is an approach to do actually art therapy or visual exposure to patients to help them recover from, for example, PTSD, to ease these symptoms. And particularly for post-intensive care syndrome, we have patients exposed to nature, and just like we are doing a recommendation system in a museum, we do preference elicitation. What happens is you give patients a set of paintings that could help them recall their ICU experience, and then you try to map this with paintings that have some healing concepts. And then they will go through a guided meditation, a guided session to actually recover. What's the problem with this? So the first challenge is the ICU experience of patients is unique. So everyone has their own unique experience, and they don't really resonate to the same set of paintings the same way. The concept we talked about, emotional and cognitive reflections that are triggered as you are exposed to visual stimuli. And the other challenge is for the clinicians. There is a huge search space, and medical professionals or clinicians have been doing this manually, and it's quite labor intensive. And they also have limited knowledge as to which paintings can actually deliver more personalized recommendation. So this is where we introduce visual art recommendation systems. So we have the same models that we kind of designed for entertainment and in a museum, but now the context is slightly different. And this is the kind of user study that we did. So you have a former ICU patient. You have healing recalling phase where we can actually view as a preference elicitation. You give them a set of paintings and they select the one that they resonate or explains their ICU experience, and then they get recommendations. And then using this recommendation, they go through a guided art therapy session. And then we compared, okay, expert curated recommendation versus recommendations created by our RecSys engines. And then we evaluated first art therapy relevant measures, which are, for example, openness to engagement with paintings, or what kind of level of immersion does the painting give the users. And there is also these PICS-related relevant measures, like the temporal affective enhancements. What was the impact on the emotional state of the patients? And of course, we also measured the classic VRXS measures beyond accuracy measures. Accuracy, diversity, novelty, and serendipity. So before we actually deploy this with ICU patients, because this is quite a sensitive scenario, we have to actually do control or safe and sensitive deployment pilot test for the sake of this. What we did is essentially we generated these recommendations for all the 3 sample paintings, and then we gave it to experts. Affective design, ICU research, and also ICU nurse, all of which have more than 15 years of experience in their respective field. And they gave a rating to the recommendations generated by all of the 4 engines, Blip, Resonate, BERT, and LDA. We avoided using CLIP because it was not really performing well in the last evaluation. So we have unimodal, multimodal, image, text, all of them here. And interestingly, you can see like the Resonate was mostly preferred. But in museum, LDA was outperforming Resonate. So the context is different, but the performance of the model is now completely different across the same kind of evaluations. And both text-based approaches are performing very badly. Let's see an example. So this is an example generated by LDA. One of the experts said there are ruins in this painting, which is not really good for someone recovering from trauma. Another example from LDA, storm. So you see, when you move from one context to another, outperforming state-of-the-art models can perform catastrophically bad and could lead to something really dangerous. So we kind of safeguard this deployment before, and then Resonate was like consistently generating recommendations that are considered safe or okay to actually be used in an art therapy. And then we moved forward with a set of expert visual and multimodal recommendations. So these are some of the examples that we have used in the study. Now we did a user study with almost 150 between subjects. Like I said earlier, we talked about the kind of studies between and within. So each patient exposed to different settings. So you have 50 for expert, 50 for visual, 50 for multimodal. And then we assessed all these measures, so engagement, immersion, accuracy. You can see the trend. Both unimodal and multimodal approaches kind of compare favorably, but Resonate tends to perform better than the expert-curated recommendations. And also, we can see an interesting trend emerging in terms of mood improvement in the patients. And if you look at this PANAS scale, which is also a PICS-relevant measure, you can see a significant improvement before and after therapy. And finally, we also did post-study participant reflection form, and then we did some sentiment analysis. And we can see that the interesting trend in terms of negative or positive sentiments within their reflection. So what is the takeaway here? Any guess? We have expert-curated sentiments. So patients who were participating in the expert-curated recommendations found to be more negative compared to patients that actually went through a guided therapy session using the visual or resonate RecSys and multimodal or blip-based recommendation. And patients in blip, interestingly, were completely happy with the recommendations. We also did something called reflexive thematic analysis. So using open coding, what are the healing concepts that were actually exposed to the patients in this recommended set of paintings? And these kind of trends emerge, which are very helpful for the task of art therapy. Now, there is a complete difference between performance in terms of context in the museum case, and then we have another performance in art therapy. Okay, so now we have RecSys performing better than experts. Then should we replace the expert? What would you do? Yes? Why? That's true. So a natural approach is to put human in the loop. And interestingly, this is what we did in a follow-up study. You have the preference elicitation, RecSys, and then you get recommendation. You give this to the expert, they get to decide. For few cases, we have positive outcomes using ResNet, but if there was one scenario where you have bad recommendation, this could end up catastrophically. So to safeguard against this, we're always going to need human, but the RecSys is kind of a support tool for the experts to actually deliver this therapy. And now let's talk about what could this mean in the long run. So we used RecSys to support the rehabilitation of PICS patients, right? But what if we solve this from the source before it's even actually happened? And this is like a Vital Sky developed by Philips in front of an ICU bed. So what if we conduct art therapy in the ICU so that the patients don't actually develop this syndrome as they are released? And yeah, or there is also a possibility of using the same RecSys engines that we developed to guide visitors in a museum or in a mobile app to actually use them in a home care or residential settings, so that like patients after released or in elderly care settings, there is a strong correlation between nature and mental wellness. So these are some interesting downstream applications that you can think of. You design a model for one case study, you apply it in a completely different another scenario, performance is different, and what you measure is also different. But the kind of measures that we employ here to safeguard safety, to ensure engagement, immersion, and while at the same time improving learning and discovery are quite important things to take into consideration. So yeah, that's the case study on healthcare, which is somehow a downstream application of RecSys from a museum. Now let's talk a little bit about some common challenges in RecSys and some issues. So first is like privacy. What do you think of privacy. What do you think is an issue in RecSys? Yeah. There's always this trade-off between getting the best recommendation versus giving some kind of personal information. If I know you more, I can adapt to your needs and interests and preferences more. And yeah. So this is something important to analyze. And another issue that is scalability and also needs to be adaptive in changing business needs. Like we said, in CPSS scenarios, for example, users change, goals change, and these evolving systems, you have to take into account how can I adapt? How can we actually inject? We were having a conversation earlier about participatory design. So you try to go to the users and ask them, what do you think is the best approach to solve your problems? How can we actually inject this back into the model so that we can have adaptive systems? And yeah, there are some issues that you can read, but how is the time? Okay. I can quickly move across these issues, and I would like to talk a little bit about something what we call echo chamber effect. So again, it has to do a lot with what is the recommender system doing to the users. So the evaluation that we are used to is how accurate is it towards their preference. But we want to ask, how good is the recommendation? But also, how good is that evaluation? What is it actually doing to the users? So the echo chamber scenario is like you have a recommendation that is really personalized and pushing users into some kind of filter bubble where they're only exposed to things that they like. They have no idea about views and alternative perspectives outside their view. So when you measure like serendipity, novelty, and diversity across this, you want to see a good strike across these evaluation frameworks. So I mean, we want to, if you really want to have a fair RecSys, I would say, we need to strike a perfect balance across these beyond accuracy measures. And one way to avoid this echo chamber. Another interesting thing that we are currently exploring is the user control. So far we have seen content-based recommendation using different models, unimodal, multimodal. What happens under the hood is you learn some embedding, you generate similarity metrics, and then you score, and then you give recommendation. This is a black box for the user. As a user, you just give your preference, and then the model gives you a recommendation, right? You have no idea what happens and why you get some recommendations sometimes. So can we unpack this and give users more control? So we saw that this user provide hyperparameters earlier. How likely are you interested to visit diverse content? This is like one input that we can use to optimize the convex combination. But what if we implement this with kind of a slider? So you can give the user to control the recommendation. Now the user is kind of in charge. But there is much more to do. We have no idea what is happening inside the recommender systems in the black box. So there are some interesting works trying to use some parameters from the models themselves to give users control. Can we actually semantically explain those parameters to the user so that they can actually see? This is an open, interesting challenge that we are currently exploring. So yeah, that's pretty much for this session. And if you have all downloaded the notebooks, then we can move on to a hands-on session. But before that, questions. Okay. We have like half an hour for the hands-on session. So go to the GitHub repository, clone the, okay. And yeah. And yeah, meanwhile, please feel free to reach out and fill out this survey. Sorry? Okay, let me. So in the repository, you have the slides and some additional reading material and some of the papers that we just discussed during the talk. And there is a folder called notebooks. Inside you have 5 different notebooks. So the first 2 are kind of introductory tutorials if you are not familiar with PyTorch and Keras, the popular deep learning frameworks. And the third one is the text-based via RecSys. The notebook is quite self-explanatory. You have descriptions of the data set. For example, in the first one, you have the pre-processing phase. Then you have a module that actually builds the topic models. And here we are using 2 different textual descriptions. So textual descriptions in this textual description. And then we have another textual description which combines these 2, the metadata and the actual semantically rich descriptions. And then we see how the topic models perform. So there is this coherence measure that you can measure to see how good of the number of topics are. So using the 2 descriptions, the enriched one is a combination of textual versus metadata, and then the description D is the blue one, is the description given by the curators. So you can decide to stop where you have a higher coherence value, and then you set that to build a topic model. And once you do that, then you can have your similarity metrics, cosine similarity metrics here. And then in the end, you can basically make a recommendation using the LDA engine module that you can find here. And here you have sample of user preference. These are the IDs of the paintings, and then these are the ratings that the user gave. So you can play with these values, change these values, and then you can generate different recommendations. What you can notice is like with few number of ratings, the recommendations don't actually change that much. So the more paintings that you rate, the recommendations start to change and get more personalized. Yeah, so and then the next notebook is doing pretty much the same thing, but now we are using BERT. You have the same pipeline and recommendation method. And the last one, the Phoebes notebook, is using Resonate. So you have transfer learning to extract features from the pre-trained Resonate using the pre-trained Resonate 50. And then you have a module here, LD Resonate engine, which basically does the retrieval for you, given this preference information. So you can try to play with different recommendations and see how the model behaves. And for the last part, the multi-stakeholder approach for the optimization, you have the full GitHub repository from the paper here. It's here. Go to the PDF, and then you can find the GitHub repository for the multi-stakeholder implementation using Gurobi.